Alright, so now we're going to look at number 8. So this one gives you a whole bunch of more new series to look at, and it's going to ask you, does this converge or does it diverge? So what we want to do is some of these look pretty spooky, but let's see. So start, this is another one I need to change, 1 to infinity of n minus 1 over n times the root n plus 1. And so the entire thing that you should be thinking when you see a series like this is, okay, there's some function that this should look like. So when I close my eyes and think of n being really big, the minus 1 on top really isn't doing much. Similarly, the plus 1 isn't really doing much in the square root. So this looks like n over n to the 3 halves. So I look at this guy and I say, okay, this is what I want to compare it to. And I know that this series diverges. So I want to show that this series also diverges. So what I do is I compare it. This is the same thing as 1 over n root 2, 1 over root n, 1 over root n, which I know diverges. So what I do is I use the limit comparison test. So I look at the limit as n goes to infinity of n minus 1 over n root n plus 1 divided by 1 over root n, and I get root n times n minus 1 over root n plus 1, but with a limit. In this one, this limit is going to be equal to, I would be fine with you just writing down this is equal to 1, because you know the powers on top and bottom are the same, and the ratio of the leading coefficients is 1, so this limit is equal to 1. Okay, so the limit is 1. So remember what the limit comparison test says. If you get a number between 0 to infinity, don't confuse this with the ratio or root test. If your number is between 0 and infinity, then you either both series converge or both series diverge. Since sum n equals 1 to infinity of 1 over root n, we know this diverges by the p-series test. The sum from n equals 1 to infinity of this new thing, n minus 1 over root n plus 1, n over root n plus 1. I don't think I've said that correctly yet. This also diverges by the limit comparison test. Comparison test. Okay. So that's part A. It diverges. And this is all about the important thing for ones like these are you kind of have to know if it converges or not just by looking at it, because you have to know what to compare it to. So here I said, okay, this looks really like 1 over root n, and I know that diverges. So that's what I'm going to compare it to. So part B, we have this really gross looking one. Sum n equals 0 to infinity, n squared plus 2n plus 4 over n to the 4th plus 3n squared plus 1. And then same story, I kind of imagine when n gets really big, on top it's really just going to be n squared. That 2n plus 4 is going to be so small. And then similarly on bottom it's going to look like n to the 4th, and everything else is going to get so small, which looks like 1 over n squared. So that doesn't show that the series converges, but now I'm thinking, okay, the series probably converges. So I say this is what I'm going to compare it to. So I look at the limit as n goes to infinity of this fraction plus 3n squared plus 1. And then I'm going to divide by the other fraction, but remember, if I'm dividing by a fraction, then I'm multiplying by the reciprocal. So I get n squared over 1. So this is the limit as n goes to infinity of n to the fourth plus 2n cubed plus 4n squared divided by n to the fourth plus 3n squared. Is that minus 1 plus 1? So now what happens? Same story. There's a 1 here, a 1 here. So this limit is 1, so the series converge together as this sum. N equals, where did it start? 0? Well, it needs to be 1 for this to work. Since this sum converges, this sum also converges. By, once again, the limit comparison test. Okay. Converges. Okay. So now we look at part C. C, sum n equals, this is another one that should start at 1. Natural log of n over n cubed. In here I could try comparing it to something. Generally what you want to think is natural log of n, that's less than n. So this is going to look less than n over n cubed. And actually I'm kind of doing the solution right now, because I'm literally going to say just this. The natural log of n over n cubed is less than n over n cubed, which is equal to 1 over n squared. This sum, n equals 1 to infinity, 1 over n squared converges. So this sum, natural log of n over n cubed, converges not by limit comparison anymore, but just by the normal, no adjective comparison test. By comparison test. Okay. So that's what we have there. And now part D. Sum n equals 0 to infinity. This one's fine. 4 to the n over 9 plus 7 to the n. So I look and I say, I kind of think this converges. And in fact, we can do the same thing. So this looks a lot like 4 to the n over 7 to the n. That sum converges because it's a geometric series. Okay. And even better, I can do the same trick I did last time. 4 to the n over n plus 7 to the n. That's just less than 4 to the n over 7 to the n, right? Adding 9 makes that bigger on bottom. Divide by something bigger, you get something smaller. And this sum converges because it's just a geometric series with r less than 1. So this sum, 9 plus 7 to the n, converges as well by the comparison test. So you can use the limit comparison test on these. It'll be fine. It's just a little more work. Whereas this was kind of nice and easy. So that's your answer. But again, you can't just say it converges and not do any work. That's worth almost nothing. The work is just as important as the answer. All right, so that is number 8.